Hey everyone, so this video is going to be on hypothesis testing. We'll go through both one sample and two sample hypothesis testing. So the general premise is we can have some sort of assumption about the population mean. Let's say we believe that it's equal to 10, whatever it is we're measuring. We think the population mean is equal to 10. And we can do a study on that. And our study shows a sample mean of, for example, 9.5. Now, does that mean that our assumption is correct or not? Right? Our sample mean is not equal to 10, but it is rather close to 10. Is it close enough or not? Or is it far enough for us to negate our hypothesis, our assumption that the population mean is in fact equal to 10? Now, what if we had a different sample mean, which was not 9.5, but 9.9? Would we be more convinced? Maybe. Or what if we had a different sample mean, which was not 9.9, but 5? Okay, then would we be convinced that our assumption that the population mean is 10 might be wrong? So the question is, where do you draw the line? And that's what hypothesis testing is about. And we'll go through the steps of hypothesis testing, and then we'll talk about how to do this in a more formal way. So the first step is you make your assumption. So you make your assumption about the population mean. Okay, maybe that assumption is that the population mean is equal to some value. Maybe your assumption is that it's less than or equal to some value. Maybe your assumption is that it's more than or equal to some value. You make some assumption. And then step 2 is you collect your data. Okay, now when you collect your data, you're going to have a sample mean, you're going to have a sample standard deviation, or maybe you know the population standard deviation. You're going to have your number of data points as well. And when deciding whether your sample mean is sufficient data to reject your assumption or not, we're also going to consider, well, what's the standard deviation? What's the sample size? That's also important because that determines how reliable your sample mean is or isn't. And then 3, you determine whether to reject your assumption. Okay, and this is how we make decisions in life. We all have our assumptions that we go through life with, and we see the world around us, and that's the data that we're collecting. That's step 2. We see the information around us, and based on that we determine, are we going to stick to the assumptions that we have about the world, or are we going to change our mind about some things and hence change our behavior? That's the general structure of hypothesis testing. Now here's how it's done formally. So, for example, a pizza shop claims they deliver in 40 minutes. Okay, that of all of their delivery times, on average, it takes them 40 minutes to deliver. Okay, so let's assume they're right. There's our population mean, and it's equal to 40. That's our assumption. Now the assumption that you start off with is called the null hypothesis, and the symbol for it is H sub 0. Okay? The alternative hypothesis, sometimes written H sub 1, other times written H sub A, this is what would negate your assumption, in this case, that it's not equal to 40. And the claim, in this case, that's made is the null hypothesis. Okay, the shop is claiming that the population mean is equal to 40. Okay, so this is called the null hypothesis. It's what we start off assuming, and this is called the alternative hypothesis. Okay, and then sometimes it's written as H sub A instead of H sub 1. Okay, and that's step 1 of hypothesis testing. Okay, you state your assumptions, your two hypotheses, right? H0 being the one you start off with, and you identify which one is the claim. Okay, now step 2, you have to determine your cutoff point. Okay, before you even have the data, you have to decide at what point am I deciding I'm going to reject my hypothesis. Okay, the data is too far from what I'm assuming. I'm going to reject the null hypothesis. And this is done using something called the alpha value, also known as the significance level. Okay, so the significance level alpha, okay, this is the probability of rejecting a true H0. So the null hypothesis was true, your original assumption was true, but you rejected it. That's alpha, that's the significance level. Alternatively, beta is the probability of not rejecting a false H0. Okay, the null hypothesis was false, the original assumption was false, you should have rejected it, but you didn't. Okay, so for example, if your null hypothesis is that a suspect is innocent, alpha is the probability of saying, you know what, they're guilty, when actually they were innocent. Whereas beta is the probability of saying, you know what, we're going to stick to our assumption, they are innocent, when in fact they were guilty. Okay, and these two errors are known as type 1 error and the second one is known as a type 2 error. Now, for hypothesis testing, we're going to be using alpha, okay, our type 1 error, the probability of rejecting a true null hypothesis. Okay, so let's say we're told that alpha is equal to 0.05 or 5%. So we're willing to accept a 5% risk of rejecting a true null hypothesis. Okay? Now what does that mean? Well, if we have our distribution of sample means, all the sample mean values we can possibly get, we know that the center of that distribution is the population mean, and that's something we know by the central limit theorem. So, anything along this x-bar axis, it's possible for us to observe a result like that given whatever population mean it is that we assume, in our case 40. But there are these two tails, okay? 0.025 is the probability that we are at the upper tail, and 0.025 is the probability that we're at the lower table. Now notice this is alpha over 2, and this here is also alpha over 2. Okay? They add up to 0.05. So, these tails determine our cutoff. Okay, if we see a value this small, that it fits into the smaller tail, also known as the rejection region, or we see a value this big, so big that it falls into the upper tail, also part of the rejection region, we say, you know what, these values are so far from our assumption that mu equals 40. They're so far from our assumption that we're going to reject our assumption. Could we be wrong? Of course we could be wrong. Of course, the mean value, the population mean, really could be 40. And we really do happen to observe a sample mean which is within that upper tail or within that lower tail. But the chances of that happening is just 5%. So, yeah, the test isn't perfect. We have a 5% chance of rejecting a true null hypothesis, but that's the risk we're willing to take. And we need to take some sort of risk like that because we need to determine what are these cutoff points. Okay, and those cutoff points we can determine using the Z table or the T table. Now we know that that central part, by the way, is 0.95 of the area under the curve because the entire area has to add up to 1. So for example, what's the Z value that will cut off this lower tail? Well, we just look up 0.025 on the Z table. 0.025. And just pick the color here. And there we are. So that gives us the Z value of negative 1.96. So negative 1.96. And then we know that upper cutoff will be a positive 1.96 because of symmetry. So whatever sample mean we get, if on the Z scale it is above positive 1.96, it's in the positive rejection region, and we reject our null hypothesis. If, on the other hand, it's below negative 1.96, then it's in the negative rejection region, and again, we reject our null hypothesis. So let's say we look at our data after doing a study. Let's say we looked at 40 deliveries. And the sample mean for the time of those 40 deliveries was 42 minutes. And the standard deviation was 5 minutes. So, are we in the rejection region or not? In order to do that, we have to take our sample mean and present it on the Z scale. And doing that, that's called our test static. So, x bar minus the population mean divided by the standard deviation. Now remember, this is the population mean of sample means. This is the standard deviation of sample means. That is going to bring our x bar to the Z scale. And by the central limit theorem, that's actually going to be equal to a value like this. Okay? And this is called our test static, right? So it's a Z value, and sometimes it's called Z test. Sometimes you might see it called Z stat. Okay, but what it is your test static. It is the value that will allow you to draw a conclusion from your test. Okay, so in our case, our test static looks as follows. We have 42 minus 40. We put in 40 for the population mean because if you recall, our null hypothesis is that the population mean equals 40. That's our assumption. We're sticking to it for now. So that's divided by 5 divided by the root of 40. And then we just do our calculation. So 5 divided by the square root of 40, 0.79. And that gives us 2.53. Okay? So 2.53 on the Z scale is going to be, let me just grab a different color for you guys. Okay? Is going to be somewhere over here. Right? That's our test static. 2.53. It is bigger than our critical value, and that's what the cutoff is called, the critical value of 1.96. So we are in the rejection region. Okay, this is a value that is very, very high given our assumption that the population mean is 40. So we're going to reject our null hypothesis. Could we be wrong? Could the population mean actually be 40? Yeah, it's possible. But the probability that it is going to be this high is less than 5%. So we're going to reject our null hypothesis. Okay? And so now we've made our decision. This is our step 3. Okay, step 2 we did right here when we collected the data. Step 3, we make our decision. H0 is rejected. And if you recall, H0 corresponds to the claim. Okay, which means the claim is not supported by the data. Okay, so that is the process of hypothesis testing. And what I'll show you next is a number of examples, each one a little bit different.